Okay, so like I said, I have a little activity for you guys to do where you guys are going to do some graphing and you're going to be kind of competing against each other a little bit. Um, Before we can do that, though, I need to kind of set a little bit of groundwork here as far as how do we graph linear and quadratic inequalities, and then we can start talking about how systems of inequalities are going to work too. Now, most of this, like we talked about earlier, is all going to be somewhat review for you, but I just want to make sure that we're all clear on certain ones and how we do it, okay? So, in general, if I had, let's say, y is greater than or equal to 2x plus 1. So this would be an example of a linear inequality because the equation, if we took off the inequality sign and put an equal sign there, that would just be a line, right? Y equals 2x plus 1. So how does the graph of y is greater than or equal to 2x plus 1 differ from just graphing a line? You guys remember? Yeah?
Any value above the line, right?
Any value, any ordered pair would be a solution as long as it's above the line. Okay? So if we were going to graph this thing, let's do a little sketch of it here. So it'd have a y-intercept of 1, it would be a slope of 2, so it'd be going kind of like this. And all solutions would be above the line, so over here. Okay, so it just looks something kind of like that. How does it change if I change it to that? What changes on the graph? The line becomes dotted. Why is it dotted? Say that a little louder. It doesn't include the points that are exactly on the line. That's the difference. This one, the boundary, the line is called the boundary because it's between what's shaded and what's not. The boundary is included on this one because it could be equal to that line. This one, it's simply greater than the line, but not exactly the line. So the ordered pairs that are sitting on the line don't count anymore for that one. So this one, I'll do another quick little graph. Should look very similar to the last one. The only difference is, like was stated, it should be a dotted line now. And then shaded above again. Okay, so any kind of a line, that's the idea. If it's less than, you shade below, get the idea. There are some special kinds of lines, horizontal and vertical lines, that I wanted to make sure we were clear about as well. So what if I had an inequality like that, x less than or equal to 2? How would I shade that region? Is it vertical or horizontal?
It's vertical.
Yeah, always start by taking away the inequality symbol and putting an equal sign in there, and then what would that look like? That's where you want to start, right? So it would be x equals 2. So, okay, so if I'm at 2, and this is an or equal to, so it's not a dotted line, it's a solid line. You figured it out eventually, though. All right, so then what side of that line am I going to shade? To the left, because all the x values in ordered pairs, that would be less than 2. So everything over here. Okay. Other type, what if I had y greater than negative 3? So what would that look like? Horizontal line, yep. At negative 3. Solid or dotted? Dotted. And then shaded above it, yeah. Okay, so linear stuff, that's about as challenging as it's going to get, okay? So then quadratics. You guys haven't done this before, but it's really the same concept. If you're going to be doing an inequality involving a quadratic, yes?
Could we factor the two linear equations and then just do it from there?
It's a good idea, but no. So I'll even put an extra little wrinkle in it here so we can discuss it. So what if it was written like x squared plus y less than or equal to 4? Okay, so we're going to want to rearrange things here a little bit so that I can actually graph it. Again, the way we start with all of this stuff is think about it as if it were equal instead of the inequality symbol, right? And if I was going to graph this thing with an equal sign, I'd want to get y by itself. It's no different. So if I subtract the y squared, or the x squared to the other side, I get y less than or equal to negative x squared plus 4. So then I need to graph the parabola negative x squared plus 4 and go from there. Yeah?
When do you have to switch the sign?
You switch the inequality sign anytime you multiply or divide by a negative number, because that would change the way the inequality goes then. But in this case, because we were subtracting x squared to the other side, we didn't need to worry about it. But sometimes, yeah, you will do that, and you'll have to be careful of that. Okay, so negative x squared plus, everybody in here, I think, can do that. How would I graph that parabola? Okay, so it's going to start up at 4, and it's going to open down. Or equal to. So they're going to have solid parabolas and dotted parabolas, just like the lines, right? Depending on if the boundary is included or not. And this is less than. So we're going to shade, nope, below the parabola, right? So if I'm going below the curve, it's going to be all of this inside of here. Okay. So we're still thinking about that above versus below idea. You don't want to think of parabolas as inside versus outside because you'll confuse yourself. Just what's below the curve, what's above the curve, and that'll work a little bit better. Okay, so what we're going to do in this little activity is you're going to have systems of these. So i.e. more than one happening at the same time. And what do you do with more than one at the same time? What are you looking for? Yeah, where does the shading overlap itself? Okay, so what we're going to do is I'm going to have 6 systems of inequalities. Some only have 2 equations. Some have as many as 6 that you're going to put together, but they're not difficult. And I'm going to have you guys in pairs, and whatever pair can get the most of them completed in 20 minutes will win Twix. And then you have to use my colored pencils because I want them to look pretty. Okay, so I'm going to give you some graph paper, some colored pencils. I'll put the problems up on the board. We'll start the stopwatch, and we'll see how many of these you can graph correctly in 20 minutes. Okay? So find a partner, whoever you'd like to work with, and we'll get started. Looking at a graph that's going to be similar to what you guys were producing yesterday. Okay? So it's going to be some kind of a system of inequalities where there's going to be a whole bunch of lines on this one. We're not doing the quadratics. It's linear programming because everything's a line that sets it up. But there's going to be some kind of region that gets produced by doing all that system of inequalities business. And in that little region, so I'll give you like a quick little example. Let's say we've got a region that's cut off by, we've got like a line going this way, a line coming down this way or something like that. And then the inequalities are such that when we do all the shading, the overlap all happens right in here. Okay, so this region then is a big collection of ordered pairs. There's a bunch of XY pairs that are all inside of that shaded region then, okay? And what we talked about yesterday is all those ordered pairs are solutions then to the system. There's not just one number or one ordered pair that works. It's a whole bunch of them that are in there, okay? So if I have some kind of something that I'm looking at that uses all of those XY pairs, okay? It's called the objective function. And the objective function actually is a function of both x and y. So we say it's f of x comma y. Okay, so it's something where we would plug in both the x and the y from an ordered pair that's in that region. and get some kind of a result from that. Okay? And the goal of linear programming is to either maximize or minimize the value that we get when we plug those numbers into that objective function. Okay? Now, if we were to try and do this just straight ahead, we'd never stop. There's an infinite number of points that are in that region, right? But the idea is that if you have this cut off by a bunch of lines, that the maximum and the minimum can only happen at one of these points. Okay? Because those are kind of the extreme, furthest on the outside points to that region. Okay? Now, you might think, well, okay, what about all these little points that are like right along the edges, that sort of thing too? But it actually turns out that where those come together and meet still end up becoming a little bit larger, a little bit smaller, potentially, than the ones that are along on the edges too. Okay? So depending on what the shape of the region is, there could be a different number of these points that we need to check. Okay? But if it looks something like this, then we'd be really just looking at these 4 then. Okay? So then from there, it's just a plug it in, see what you get for each one of them, depending on if you want to maximize or if you want to minimize something. Okay? So how does this fit into like real life stuff? Well, okay, so here's where I'm going to try something and see if it works or not. Does anybody here work on or have a family that works on a farm or something like that? Okay, so you guys can help me out here. Okay? So what do you guys produce on said farms? Apples? Corn, wheat, hay, meat. Okay. So I need a farm that produces 2 things. So maybe the corn and the wheat. Okay. So is there a minimum amount of corn and a minimum amount of wheat that you have to produce, or not?
Yeah.
Okay. So can you give me some numbers that I can use for that then?
Like probably 10 acres corn, 10 acres wheat.
So what does that boil down to, like when you actually like sell it?
Like dollar amount or?
Like, do you have it like in bags or bushels, or what do you sell it in? Yeah.
Probably 2,500 bushels of corn, 1,000 bushels of wheat.
Okay, so say that again.
2,500 bushels of corn.
And this is minimum, right?
Yeah.
Okay, so 2,500 bushels corn. Okay.
And about 1,000 bushels of wheat.
Okay, and this is all at least.
Yeah.
Yeah. Okay. Okay. Is there an upper limit to how much you can produce of each of those 2?
Yeah, I guess.
Okay.
You get one about a spade.
Right. So can you give me like an estimate of about how much of each of those?
Probably 10,000 bushels of corn.
Okay.
4,000 bushels of wheat.
Okay, and that would be at most. Okay. Is there any kind of constraint as far as, like, when you ship it out, like like a minimum amount that you have to ship out, or does that not matter?
Semi-trailer is 1,000 bushels. So.
1,000 bushels of whatever. They're about this. They're the same size, so it doesn't matter. Okay. So let's make sure that we're comparing, not to use a pun, but apples to apples here, even though they're not. How much you produce like in a season?
Yeah.
Is that what this is? In 1 year?
Yeah.
Okay. So the amount that you could transport, could we break this down into how much you could do like in a day, or does that not really make sense for what you're doing? No? Okay. So the transportation issue, if you're talking over the course of a year, because you're talking like each semi, what it can take, is there a limit on that, like over the course of the year then too, or not?
Not really.
Not so much? Because you could just keep going with it as long as you need it to do. Okay. Because to make this really work, I need one more constraint that's not just the at most, at least stuff too. So is there any other constraints to how much of each you can produce at all, based on like people working on the farm, that sort of thing, or anything we can do with that?
The amount of land we rent sometimes will
Mm-hmm.
Throw that in there.
All right, we'll see how we can do that then. So let's say that, and I'm just going to make something up here a little bit just so it kind of fits what we're doing. So let's say over the course of a year, based on land constraints, you can only produce up to a total of, based on the numbers you gave me, let's say maybe 10,000 bushels of both. Okay. Of not each, but like together. So together, we're only going to be able, for maybe this year the weather was bad or something or whatever, the land, the soil wasn't working the way we wanted it to or whatever, and we're looking at, okay, we're only going to be able to get 10,000 total. I was trying to use the transportation thing to make that work for me, to have a total of both together as a constraint, but we'll try and go with this and see if it works. So we're going to take all this information now. Oh, wait, one more thing I need from you. How much do you make per bushel of each?
That varies a lot.
Does it? Can you give me like an average?
I would say maybe a buck or two average. Yeah, maybe.
Is corn more profitable than wheat, or are they the same?
Well, corn yields higher, but you have a lot higher input costs.
Okay.
So in the end, it ends up not terribly different.
Okay. Can I just make up some numbers so that they're different, so that it's more interesting? Okay. Which one do you think probably give you more profit?
For our ground, it's usually wheat, just because we can raise a lot better wheat than we can raise corn.
So we want to say like $1.10 for wheat and $1 for corn, something like that. Okay. Per bushel, right? Yeah. So $1 per bushel profit, and the wheat maybe like $1.10 per bushel profit. Okay, I think I got everything I need that we can make this thing work now. Everybody cross your fingers. So we need to now put this into math speak a little bit. Put some variables in there, make some equations, some inequalities based on what we've talked about for each of these different things that we've come up with here. Okay, so just to kind of relate this back to what we were talking about, all this information that he gave me right here, all this stuff is what we call constraints. That's how you heard me using that word, right? What are the constraints? And these are all like limiting factors to how much of each we're allowed to have. Okay, and all of these are going to become inequalities then. At most this, at least that, blah, blah, that sort of thing, right? And all of that is going to help to produce a little region right here like we did yesterday. This is what we're interested in, right? We want to, in general, the goal is to maximize your profit, right? When you're working on a farm, right? Just like any place you work. So this down here, this profit information that he gave me, we're going to use that to make our objective function then. The thing we're trying to maximize or minimize. In this case, we want to maximize it. Okay? So here's how we can take each of these bits of information and turn them into stuff. Or let's see if you guys can help me out. So let's say that X represents the corn. So that would be the number of bushels of corn. And let's say that Y is the number of bushels of wheat. Okay? So this is how we're going to kind of encode everything that we're talking about. So up at the top here then, we have at least 2,500 bushels of corn. So can you turn that into an inequality for me then? Does that make sense, everybody? X has to be greater than or equal to 2,500. Okay, what about we have at least 1,000 bushels of wheat? There you go. Yep. And I bet you can probably riddle these out now too then, right? X has to be less than or equal to 1,000 or 10,000, and Y has to be less than or equal to 4,000. Okay. How about this one? Over the course of a year, based on the land constraints, you can only produce up to a total of 10,000 bushels of both. You got it. Okay, so those are all of our little linear constraints that we're going to have. And then our objective function. Instead of doing f of x comma y, I'm just going to use p for profit. So what would be the profit equation then? Yeah, 1x plus 1.1y. Okay, so however many bushels of corn I produce, I get $1 each, so 1 times all of those. And then every bushel of wheat, I'm getting $1.10, so 1.1 times that. Does that make sense? Okay, and that's not equal to anything yet, because remember, this is the one we plug into to figure out what's the profit each time to try and maximize that. Okay, so having that with actually 3 variables is not a problem. We need the x and the y to plug in, and then we figure out p for each one of those. Okay, so let's do the same work we did yesterday. We got really big numbers here, though, to figure out our feasible region. So since our numbers are really big, do you guys care if I just chop them down a little bit? So, because he's talking about things in thousands of bushels, right? Yeah, I'd rather do that. It would make it a lot easier to try. So go with that. Just remember when we get to our answer, though, we're going to have to then put the zeros back on. But so for this, let's just do x greater than or equal to 25. This will do y greater than or equal to 10. So yeah, I'm just dividing by 100 for each of these then. So this will be x less than or equal to 100, y less than or equal to 40, and then this equation, x plus y less than or equal to 100. Okay, and the equation we're going to leave alone for right now. Let's sketch a graph of what we got here. See if we can make this feasible region, is what it's called. So everything's positive. So, and when you're working with linear programming, like 99% of the time, it's going to be everything's positive because you're talking about positive amounts of things. So it doesn't really matter to just get rid of the rest of the coordinate plane then. Okay, so I'm not necessarily going to make everything to scale here, just for the ease of drawing this thing, but do the best I can with it. So we're going to go up to, on the x, we got to get up to 100. So maybe if we count by, I'll go by 20s, sure. So yeah, that gets us to 100 here. So we got to have x greater than or equal to 25, but less than or equal to 100. So we've got this vertical line. This is our, this is x equals 100. And then we've got another vertical line that's got to happen at 25. So that's like over here somewhere. Okay, so remember this is for our corn, right? So x is corn, so we're like caught in this little corridor here now. It's got to be just stuff that's in here. Can't be any less than it, can't be any greater than it. It's got to get stuck in there. And then for wheat, we'll do the same thing going the other way. So we're going to have to go everywhere from 10 up to 40 on that one. So we count by 10s on that side. Okay, and then we got 40. Okay, so we're really, so far, we're in this little rectangle, right? all the little ordered pairs that could work are in the rectangle. This constraint right here. Okay? So x plus y has to be less than or equal to 100. How would I graph something like that? What did we do yesterday with those? Yeah, if we want to be able to graph it, it's got to be what starts it? Y, yeah. So we'll just rearrange here a little bit. We're not negative 1, so we don't have to worry about the sign change there. So negative x plus 100. So I got to start up at 100. Didn't leave myself a lot of room there. The y-intercept and the x-intercept are both going to be 100. So it's going to do something kind of sort of like this then. It's going to come up this direction. And really, like we talked about, the only important thing is being able to identify where the shaded region is and then where the corners of that region are. And we can still do that with what we've got here now. So if we look at this thing, it has to be less than this line inside of this rectangle we created, right? So that shaded region then is this. All right, and we are interested in these 4 points. And each one of those points represents a combination of corn and wheat, bushels of corn and wheat, and then we'll take each one of those combinations, plug it into our equation, see what we got. Okay? So here, that is the ordered pair. Let's see, x was 25 there, right? And the y is 10. So it's 25, 10. So into our equation, though, let's make sure we actually convert those back to the numbers we had. So this would be 2,500. This would be 1,000. So it's going to be 2,500 plus 1.1 times 1,000. Okay? Don't need to crunch the numbers just yet. We'll set all these up and then we'll crunch them out real quick when we're done. What are the coordinates at that point? 2540, okay. So 2540 equation, 2,500 plus 1.1 times 4,000. Okay, then we got this guy. Now that one's a little bit more tricky. So where exactly is that coordinate, or how could I figure out where that is? It's the intersection of 2 lines, right? So how would I figure out where that is then?
Take the 2 equations with that model of the line and set up a system of equations.
Yeah. So I've got, in this case, so I'll come over here and do this. So I've got this diagonal line is this one right here, right? All right, and I'm not concerned with the inequality anymore, right? Because I just want to know where they cross. So y equals negative x plus 100. And then what's the other line that's crossing it? Y equals 40. So yeah, it's a system, but it's a pretty darn easy one though, right? I mean, you just do a simple substitution and you can get the x for that pretty quick. So if we plug the 40 in, 40 equals negative x plus 100. Let's see, you could add the x, subtract the 40. So x should be 60, right? Okay. So, yeah, graph is not to scale, like I said. All right, so x is 60, y is 40. So our profit there is going to be, oops, not 2,500 anymore. So that's going to be 6,000 plus 1.1 times 4,000. This one down here, which is another system, right? It's going to be that same diagonal line, but this time the y is not 40. What's the y? It's 10, right? So if I'm just going to go back into here and just change it, okay? So this would be a 10 now. and that would make this a 10. So what do we got then? So that'd be 90, right. So x is 90, and y is 10. Okay. So profit, 9,000 plus 1.1 times 1,000. All right. So quickly, take out your calculators, type them in. Let's see how much corn and wheat we should produce here. Maximize our profit. You might be able to look at those and take a guess, but let's work them out anyway. So I'm going to go ahead and freeze this. I'll do it as well. Let's just see if we come up with the same stuff when we're done, and we'll have our answer. All right, anybody need more time? Are we good? I don't want to let the cat out of the bag too quickly, but if we're all just waiting on me, looks like we're good. Okay. Oh, here's what I got. So the 60-40 wins, right? So $10,400. Now this one was pretty close, $10,100. So both of those would have been decent options. But yeah, it looks like based on our results then, if all of these constraints were, true, then we would want to produce about 6,000 bushels of corn and 4,000 bushels of wheat to make this profitable, or make a Well, sometimes when you look at the feasible region, it can be obvious. Like, in this case, we're getting things, so we're going to want ordered pairs that are as much like up and to the right as possible. Does that make sense? Because we want both x and y to be as big as we can working together. But sometimes there's a little bit of nuance based on how much you're getting. Like, that's why I wanted to make the for each one, so that it wasn't going to be like painfully obvious which one was the right answer, because we're getting a little bit more out of the y than we are the x, so it doesn't really balance it off quite exactly the same. So then, to be sure, you really need to plug stuff in and check it out. Like, we had two that came out pretty close, so just to look at the region, I could say it's going to be one of these two, and right? But to be really sure, then you'd still need to check it out. In fact, the one that I had ready to roll too, one of the two, they had some graphing calculators, and one of the calculators gave you a profit. The other one actually lost you money. So that objective function that you were looking at, the equation, on one of them. Okay? So in that case, it's even less obvious what you have to do. So really, to kind of cover your butt on this thing, you have to do all of them and check it out and see. Just, it's really only one way to be absolutely sure about it. So, but anyway. Question? Yeah.
So you could just look at the top rightest most point. Rightest.
But how's the top point though? That's the thing. So sometimes it's really obvious, sometimes it's not though. So yeah. But stuff makes sense, guys? Together? Okay. Cool. So it's loose on your homework the rest of the time here then, and I'll be around to kind of help you out as needed. It's mostly doing the graphing stuff like you guys had from yesterday. A little bit of linear programming in the mix too, though. Okay, so stop the recording.